Here is this week's tutor session, and we will go through the weekly questions at 6. And as there's no students here, so I hope you will all watching this recording. Let's begin. So basically, this graph is what Peterson graph looks like. It has some features there. It has totally 10 vertices and 15 edges. And for all the vertex, the degree of vertex is 5. And the shortest circle length inside the graph is 5. So it means you cannot find any circle with length less than 5. Okay, so to check if it's a Hamiltonian circle, we can first suppose it is a Hamiltonian graph. And then we first create the graph here. So V1, V2, V3 to V10, and then back to V1. This is a Hamiltonian circle with 10 vertex. And with 10 vertex, the length of the circle is 10. So it means that if we can add 5 additional edges into this graph and convert it back to the Peterson graph, then it means Peterson graph is a Hamiltonian graph. So let's try to add these 5 additional edges. Let's put all these edges inside a set called E prime. And we know that the E prime is with five edges. So I want to make some claim. First, no two edges will share one vertex in E prime. Why? Suppose if it shares, so suppose there is a vertex use V1 and there's another vertex use, an edge use V1 and another edge use V1. Then the degree of V1 should be at least 4 because in the circle it has 2 and then 2 edges use V1, which is contradicts to this future. Sorry, this is 3, not 5. So we know that this claim is correct. And because claim 1 is correct, this means the E prime with 5 edges will use all the vertex. Because they cannot share vertex, so each edge will cover exactly 2 vertex and totally cover 10 vertex. And here are only 10 vertex, so it will cover everything. Then claim 3. If there's some additional edge connect V and W, the distance of V and W in the circle should be at least 4. Why? Because suppose we connect something with just length distance 3, like V1 to V4. Then we'll create a circle with V1, V2, V3, V4, and then back to V1. This circle with length 4. And the shortest circle length should be 5 in Peterson graph. So we cannot do this. And as it's a circle, so distance more than 4 means distance should be 4 or 5. Because the maximum distance is 5 in the circle with 10 vertex. And then the next claim is at least one pair of vertex VW with the edge in E prime should be with distance 4. Why? Here, this graph shows how the graph looks like if we connect all the vertex with distance 5. And this is the only choice. Then what will happen? We will create this circle, V1, V2, V7, V6, and then V1. This circle with length 4. So we cannot do this. So we know there must at least one vertex with one edge with vertex distance with is 4. Then what will happen? Let's connect some edges here. So for example, let's connect V1 and V5. We know their edge distance is 4. Then let's see where can V10 connect to. Can it connect to V4? No, because if we connect them, we will create a circle from V10 to V1 and then V5, V4. Something like this. This is also a circle with length 4. So this is wrong. Can we connect to V5? Of course, no, because we cannot share a vertex. And can we connect to V6? No, because it's also create a circle with V10, V6, V5, V1, and V10. Then can we connect to other vertex? Of course, no, they have distance smaller than 4. Then it means we cannot use V10. That means it contradicts to this one. So Peterson graph is not a Hamilton graph. Okay, we are done for question 1. Now let's go to question 2. We know that there are in power in minus 2 trees there, but how many Hamilton graphs are there? It's hard to get that, but if we can find some lower bound, like we can find some h prime, so if we can prove that h prime is smaller than h, but it's larger than t, then it's also okay. Here I just give you what h prime is. H prime is the set contains all the graph with exactly this circle. It contains this circle from 1 to 3 to 4 and then to n and back to 1. So of course, all the graph inside H prime is a Hamilton graph because this is a Hamilton circle. And of course, it's smaller than the size of H because it cannot contain all the Hamilton graph. There are many other Hamilton circle possible there. But what's the size of H prime? We know that within vertex, there are totally n choose 2 possible edges. And for now, we have decided n edges because they are in the circle. And we can decide whether the other edges are there or not. So this is the size of H prime. And this one is already larger than n power n minus 2 when n is larger. So well done, we know that Hamilton graph is more than the tree. Okay, let's go to question 3. Basically, it's just an edited version of Huffman algorithm. What is the Huffman algorithm? We first ordered all the words with the frequency, and then we choose the one with the least frequency and make them consider them as 1. Remove them from the list and add a new one, which means there are 3. With the frequency be the sum of these 3. And this 3 should be in the child, the lowest child leaf of the tree. But keep doing this until this list is empty. We create this tree, and this tree should means our prefix. However, there is a problem. Just consider if we have only 2 digits, each time we remove 2 elements and then add 1 element. So it will always finally from achieve 1 and then achieve 0. That's okay. And let's consider 2 scenarios. Firstly, if we finally left only 5 elements, which had 3 and add 1. And then we remove 1 to 0. That's okay, right? Because we create something like this one. We call it A, that's called A, B, C. Oh, let's call this maybe A, B, C, D, E. And then we got that B, C, F. Then we create this. Oh, sorry. A, B, C, D, and suppose A, B, C is the 3 least frequent one, and we combine them and create F. So then we create D, E, F, and then we create nothing. So it means we finally got something like this. Got D, E, F, and F means A, B, C. This looks good, right? But suppose if we only got 4 finally, B, C, D. And then we take A, B, C and create E. So we got D, E. So when then we can got nothing, we can got only 2 things here. So we got D, E and E, B, A, B, C. You see what happened there? We waste this digit. And with this first digit, this is a really big, huge waste here. And you can easily check this one, it's not the most efficient way. So while this may happen, because instead of take 2, we take 3 and add 1. So each time our list size will minus 2 instead of minus 1. How to avoid this situation? The idea is also simple. If at first we have odd number of list size, then we just do whatever we do here. But if we have even size, for the first round, what we do is instead of take 3, we take 2. So like A, B, and C, blah, 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 blah. Instead of take A, B, C, we just take A, B and add 1. So this will make our tree looks like something like 3, 3, 3, all the above thing with 3, and only the last really deep one with 2 things here. This will not waste anything, so this is the most efficient way. Okay. Cool. Let's go to next question then. For question 4, if you do this one, you will feel like the last question for the midterm is really easy. So for the first question, it's also easy. It's just a complete graph have the most perfect matching. Because for all the other graphs other than complete graph, they are just subgraph of it with the same vertex set but less edge set. So any perfect matching of other graph should also perfect matching for the complete graph. So it should always have the most perfect match. Then question for a tree, what will happen? Consider if some tree have a more perfect matching. Then consider this if, which vertex can it match to? It can only match to its parent, right? Because this parent is the only one connected to it. So if it has a perfect matching, we can simply match all the leaves to its parent. Then remove this leaf with this parent and redo this. By redo this, we will create a tree with n over 2 pair, right? And there's only one way to create this tree because each one just have only one match, exactly one match if the perfect match exists. So which means the perfect matching and this tree is 1-to-1. And each tree have exactly one perfect matching. So the answer is 1. And if you want to give an example, then that's really easy. A path with even vertex have a perfect matching, and it's easy to show that. Yeah, something like this. Yeah, so it's easy to show that. And also, if you want to, also there are some tree with no perfect matching, so straight 0. And if you want to give an example, any tree contains some structure like this. Here is 2 leaf and connect to 1 parent. It has no perfect matching because both the leaf U and W want to match to V, but V can only match to one of them. So the other vertex cannot be matched. So it cannot be perfect. Okay, good. We go to next question then. Let's consider a simple scenario. Suppose we don't have airport at all. What road we will like? We will not like any circle, right? Because consider if I already create this 2 road, I don't need to create this road because this 2 country is already connected. So this one is wasted. So that means after create all the road. What we have should be a tree. Oh, this one is also not needed. So then how to find that? As each edge is with some cost, so we want a tree to cover all the vertex, and that is the minimal spanning tree. And the algorithm to get this is easy, and you already learned that in class. So please check that in the lecture note, and let's go on. Let's consider the scenario with two airports. What's the airline be like? In the first thing, if we don't consider the cost for the airline, it's just a additional road with cost zero, right? So what we do is for all the pair of country, we add an edge there with cost zero edge there, and then find the MST in the new graph. Okay, so after we find all the MST for all the situations, then we just choose the minimum cost MST and use that airline. Then with this idea, it's really easy to extend this algorithm to the situation we need to consider the cost for the airline. Instead of use cost zero edge, we use the cost Cij edge for ij. And do the same thing. For each pair, we add an edge there and then check the minimal spanning tree. And then finally compare all the pair for the minimal spanning tree and choose the least one. Okay, this is question 5. Till now, most questions are really easy, but then we will come to some really hard questions. Okay, we come to question 6. Consider if there's some graph G, there is no triangle G, but it has as many edges as possible. So no other G prime with no. So let's say for all the other G prime equals to G. No triangle G prime equals to G. E prime is smaller than or equal to E, where G prime is V prime E prime, and G is V. Okay, so let's suppose this one, and then I have two claims I want to show you. The first claim is the vertex in G can separate into two sets, which is S1 and S2, so that there is no any edge where inside S1 or inside S2. And for any pair of UV in different sets, there is an edge contact set. Why this is true? That's true. I can try to prove this one by try to create this one. First, we randomly select an item, vertex V in G, and then put it in S1. And then I put all the neighbor of V in S2, and then all the other things in S1 and then in S2 by repeatedly do this one. And let's use the induction to show this is always can work. So the base case is if we put a V here and if we put in V here, then these two features maintains correct for now. Because we have an edge to all the neighbor of it, and there should be no neighbor of it connect to each other because there's no triangle. Then suppose at some time, when we want to put a U inside S1 and we cannot put in, I cannot put in it. Suppose U is some neighbor of W and W is in S2. So we want to put the U in S1. Then if we cannot, what does that mean? The first question is, the first possible scenario is you already have some edges connected to vertex in S1. But let's say V in S1 and U connect to V. Is that possible? No. Why? Because then UVW would form a triangle. Because V is already in S1 and UW is already in S2, and there should be edges between V and W. Because this is our induction hypothesis. Our induction hypothesis is all the previous thing works fine for these rules. So this is not possible. So then the second possible case is that there's some V in S2 and there's no edges between U and V. This is also not possible because if we add the edge between U and V, we will not create any triangle. So this one is not true. We can simply add this edge and create another graph with no triangle but have one more edges there. So for all the cases, we can always go on this one and separate the vertex into these two sets. Then what will happen? How many edges are there? We don't know, right? Because we don't know the number of vertices in S1 and S2. But here I want to make a claim 2. Claim 2, what is claim 2? The set between the difference of S1 and S2, let's say S1 minus S2, should be at most 1. Why? Suppose, let's say if S1 is larger than S2, larger than 1. So let's suppose this one. This is minus, sorry. Suppose this one is true. Then what will happen? If we move any element in S1 to S2, and then let's recreate all the edges based on the rules, we will create another graph with no triangle. But what's the edges number of there? By removing one thing, so basically then we'll create this E. By remove one element from S1, we will remove S2 number of edges. But then by add this element in S2, we will have S1 plus 1 edges here. Then this means because S1 minus S2 is larger than 1. Oh, sorry, this is S1 minus 1 because S1 is 1 less because we remove 1 from S1. And because this one is larger than 1, so it means we create a new graph with more edges but still with no triangle. This contradicts to this one. J is with the most edges there. So it means that the difference between, so consider there are n vertex, then it means S1 may have n over 2 and S2 would have n over 2. One is upper bound and one is lower bound, no matter which one is which. And the number of edges there is the multiplier of these two things. Then basically we are done, right? Because what is question 6 ask? M is smaller than or equal to n squared over 4. And here is the maximum thing. Maximum thing is n squared over 4. Okay. Let's go to next question. For question 7 and 8, we will do it together. First, let's first prove that if there exists a perfect elimination, then there must be no circle with length more than 4 but with no chord. And we can prove this by making a contradiction. Suppose there exists some perfect elimination like this with 0 to vk. And then there we have a circle with no chordal inside it. So the circle is like C0, C1, C2, blah, 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 and C0. Then let's check which the first circle thing, the first vertex in the circle appear in this elimination. Let's say it's C1. Then what's the adjacent set of C1? Right adjacent set of C1 will be like, to show the contents at least C1, C0, and C2, right? But as there is a circle with no chordal, so there's no edge between C2 and C0 and C2. So it means this set cannot be a clique. And that contradicts to this is the perfect elimination. So no such circle exists. And that means that if there is a perfect elimination, then the graph must be a curved graph. Okay, then the reverse thing is much harder to prove, and let's do that together. First, I will give you a definition. A symmetrical vertex is a vertex which all its neighbors and it will form a clique. So basically, in a clique, all the vertex is a symmetrical vertex. And if we can prove that if all the chordal graph have a symmetrical vertex, then we are done. Because then the algorithm is really easy. For any chordal graph, we take the symmetrical vertex, put it in on the first of the elimination, let's say it's V0, and then we remove it. And the left graph should also be chordal, so there is another symmetrical vertex there. And we put it, and then we remove it. And we do this until we find all the graph G is empty. So if we can prove that if all the chordal graph with a symmetrical vertex, then we prove that there is a perfect elimination. But how to prove that? Here I will introduce another tag, a separator. A separator is a subgraph, induced subgraph of the graph G, which separates the G into different connected components. And all these other components should be disjoint, and they can only connect to the separator. And also, if the separator S separates two vertices A and B, like they in different connected components and they are disjoint, then with the separator is the AB separator. Why we need this one? Because we want to show another class. Okay. Let's consider the minimal separator, the minimal S. Minimal separator of any A and B should be a clique. Why? Because if it's not clique, then there exists some point, let's say X and Y. There's no edge between them, right? Because it's not a clique. We can always define these two vertices. Then what will happen? As it connect to A and A, we can find something. It must be neighbor of A. Because if it's no, we can remove that. Oh, by the way, the minimal separator means that it's the smallest separator. No other AB separator is the subgraph of it. So all the elements in in this separator should be a neighbor of A and a neighbor of B. Because otherwise, we can remove this vertex and the separator is still there. Right. So for minimal separator, the vertex X and Y should be all the neighbors of A and B. Then you see what happened? And there's no edge between X and Y. So the circle from X to something inside A and to Y in something inside B should be a circle with at least a length 4. And if we choose the shortest circle, the shortest path from X to Y, path A and path B, then there is no chordal. So basically we can do something like this. So we create a circle with no chordal and with length at least 4. So this means any minimal separator for a chordal graph is a clique. Then what can we do? With this idea, we can prove that there are always a symmetrical vertex in the chordal graph. And to be honest, we can prove a more strong thing. Either this graph, for any graph, It is either for all the chordal graph. It is either a clique graph or there is some AB disjoint each other. So AB is not connected each other and they are all sympodic graph. Sympodically short vertex. So how can we do this? We can do this with the induction. So let's first for the base case. Consider a graph with only one vertex. It's a clique, right? This is our base case. And then our induction hypothesis is for all chord G is smaller than G prime, or G prime is smaller than G, and chord G prime. It follows these two rules. So let's try to do the induction. If chord G is a clique, then we are done. And if not clique, we can find some point AB is disjoint, right? Because it's not clique, so we can always find some AB is not together. And then let's find the separator, minimal separator of them. That's called S. And let's call this component A and this component B. We don't care for other part. And let's consider AUS, sorry. The induced graph of AUS is also a chordal graph, right? And then let's say if it's a clique, then A is the clique. A is the symbolical point we found. And if not a clique, then we must find some A1 and A2 inside AUS. And these two should be disjoint. And they two are both symbolic graph, symbolic vertex. And another thing is A1 and A2 cannot both in S. Why? Because S is a clique, we proved before. So all the vertices in S should be connected to each other. And A1 and A2 are disjoint, so at least one of them should be out of S. So this means suppose A1 is in A. So A1 should also be a symbolic vertex in G, right? Then we found a symbolic graph in A, no matter if it's a clique or not. And we can do the same thing for BUS. And then find a symbolical vertex in B. Thus, we find two symbolical vertex there, and then this means that this induction is correct. Thus, we are done. We prove that if there's a chord graph, then there must be some symbolical vertex inside it, and that means we can easily find a perfect elimination order just by take out the symbolical vertex, and then for the left chord graph, take out the symbolical vertex. Then for the left chord graph, take it, and keep doing this. We will create an elimination order. Okay, is that okay? Let's go to next question now. Okay, consider this equation system. We have m equations and n variables. And let's call OMN be the operation we need with m equations and n variables. If we have only one variable, of course we don't need any operation. So what's the recursive thing? How can we eliminate one variable here? To eliminate one variable, let's say we want to eliminate x1. We need to make all the say some one to the same value, and then values add or minus between all these equations, we can eliminate x1. to make all these three things be the same thing. So as we have m equations with the m multiply operations, and with this m equation with the m minus one addition or minus to make this thing. So then we have n minus one variables and m minus one equations. So we can got this equation. This is our answer for question 9.1. Okay. Well, question 2, this is not hard. Consider a tree. Let's check the leaf thing. This leaf thing is only connected to its parent, and there's no other edge connected to the leaf. So there is the equation. Let's say this is x and this y. This is consider only x and y. Something like this. It means that we can use y to represent x, the value of x. So basically x equals c3 minus c2y and over c1, something like this. And then rewrite the left system of formula and then remove this thing. Remove this variable at all. And if we keep do this one, we remove this leaf and remove this leaf and remove this leaf, remove this leaf, remove this, remove this. Finally, we'll use the root variable to represent everything. And then it's easy to solve, often there's no answer. And if there's infinite answer, then just choose random one, and then anyway, it's easy to solve this system, right? Then consider circle. If the circle with length more than 3, then let's consider this vertex, this is x, and this is y, and this is z, let's say. As there is x only connect to y, and there's no edge between y and z. So we can have two equations, like cex plus c2y equals c3, and c4x plus c5z equals c6. So with this equation, we can use the value of y to represent the value of x. So use variable y to represent the value of x and substitute x in the other part. And then with this thing, we will create another equation with only z and y. So basically, we will create a new circle by doing this with one left side, and there is y, this is z. And by keep redoing this one until we got something like a circle with 3. Because if with 3, it's possible that all the 3 variables are in one equation. Then we can just use what we do in 9.1 to solve this. Okay, that is also easy. Let's go to next question then. Okay. Consider we have two disjoint circles and there's no other circle at all. What does that mean? As we only have the two circles and they're disjoint, it means that we can find some system of equations represent exactly one circle inside this system of equations. Why? Because if there's something more thing, like if we have something more like this, like some equations with not only with at least two variables inside the circle, then we'll create another circle outside the circle. So we don't have that, and we can find the two circles the system of two circles. So that means we can use what we do before to solve these two circles. And then all the things are left is represented by these two things. Or maybe something. So basically, all the things connected to other circle things is can consider as the tree rooted as the circle part, circle vertex. So if it exists something like this, there's no other circles because. So we can first solve these trace things and make it back to this circle. And then solve the circle things and make it back to tree between these two circles. And then solve this tree. As we know the algorithm how to solve the circle, and we know the algorithm how to solve the tree, this is easy. Then finally, let's go to the DAG things. Let's go to the DAG things, the DAG things. So basically, if we have something like this one, we can create some order there. Like if A is the edge between A to B, then A is always before B. We can create this because this is there is no circle inside the directed graph. We can always do this. Then what happened? Then what will happen? Suppose we have this one, then we have, let's give some name, 1, 2, 3, 4, 5. We have 1, 2, 4, 3, 5. Yeah. The order looks like this. Then we can use something before 5 to represent 5, right? Because all the variables connect to 5 is before 5. So we can use, in this example, it's only 4. So we can use 4 to substitute 5 and remove 5 here. And we got this. And then we can use the previous thing to represent 3. For this one, we can use 2 and 4 to represent 3. And then we remove 3. And then for 4, we can use 2 to represent 4. And then we remove 4. And by doing this, we keep eliminate one element and one element. And finally, we will eliminate all of them. And this why this one is efficient. Because we know that the in degree is at most 5, which means we can use at most 5 variables to substitute the last variables. Because there is only 5 in degree things connect to it. And there should be no out degree, no out edges connect to the last edges. So which means the degree of the last element is always smaller than 5. Okay, let's go to next question. This question is also simple. Firstly, consider if we want our vertex cover should be with k vertex. Then how can we create that thing? We can create a graph with k plus 1 vertex, but this is a complete graph. So basically, let's call this vertex V1, V2, V3, and 2, K plus 1. Why we want this to be a complete graph? Because we need exactly k vertex to cover everything. Because if we have less than k vertex in the vertex cover, that means we will miss at least 2 vertex in this complete graph. And these 2 vertex will have an edge between them, and we cannot cover that edge. Then this is not a vertex cover. So if we have this, we already have vertex cover with k plus 1. But we want vertex cover within vertex. Then what was k plus 2 and 2k within? We can just add them there and connect them to V1. And then we can just replace our vertex cover with like V1, V2, and it to VK. Because V1 is included, so all the other part of this graph should already be included because all the edges are connected to V1. Then we are done for this. Okay, that's all for this week's tutor session. Thanks everyone. Bye.